Hey everybody, welcome back. This is section 12.8 on IUPAC nomenclature for alkanes. Our goals in this section are that given the structural formula, to be able to name alkanes using the IUPAC rules. So IUPAC stands for the International Union of Pure and Applied Chemistry. They're basically the people that are in charge of naming chemicals. So we're going to follow the official IUPAC rules for naming alkane compounds. So it's a formal set of rules for naming alkanes, and it's really useful because if everybody follows the same rules, then you can read a chemical name no matter who wrote it and where they wrote it. So we're going to learn how to name continuous and branched chain carbon chains. That's inside section 12.8. And these you use a prefix to denote the number of carbons in the chain with an ane ending to the prefix. We're also going to learn how to name branched alkyl chains. That'll be in section 12.10. The general concept in this area is to name first based on the longest continuous chain, and then you name the branches that come off the longest continuous chain. And there's rules for naming branches based on the location and the first letter of the branch name. And then we'll also learn how to name cyclic carbon chains, cycloalkanes. And they're named a lot just like regular alkanes, acyclic alkanes, but we add the word cyclo in front of their names. And that'll be in section 12.13. So when you're naming a continuous chain alkane, this is an alkane where you can take your pencil and trace the structure of the alkane without lifting your pencil once. You name them based on how long the chain is. And we use a prefix based on the chain size, and then we add the ending ane, which shows that there's only single bonds located between all of the carbons. So for example, we had the structure this, you would count how many carbons are in the longest continuous chain. So you trace it, and if you don't have to lift your pen or pencil or backtrack, then that's a continuous chain. So here we go, 1, 2, 3, 4, 5, 6, 7, 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. So a continuous chain with 8 carbons gets the prefix oct. And then because we only have single bonds, we end the ending ane. So this would be octane as the name of this compound. Oct means there's 8 carbons in a chain, and the ane ending means there's only single bonds. As I mentioned in a previous lecture, if we had something like with the double bond in it, then you name it basically the same way. This has 1, 2, 3, 4, 5, 6 carbons in it. So it would get the hex starting, but because it has a double bond, it would get a ene ending. And if it had a triple bond, it gets a yne ending. So hexene and hexine. So the ending of the word tells you if there's any double or triple bonds. And then it can get more complex with double or triple bonds because you use a number to show at what carbon is the double or triple bond located. But in this chapter, we're just dealing with alkanes, which means that we don't have any double or triple bonds. So at the end of your chain name, you add the ane ending. So another quick example. See if you can name this one. So the first thing you want to do is figure out how many carbons are in a row. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10, so it's going to be dec, and then we end the ane ending. So this will be decane. So for continuous chain alkanes, that means you can trace the whole molecule without lifting your pencil or backtracking, that there's no double or triple bonds. You name them based on the chain size, how many carbons are in the carbon chain, and then you add the ane ending. So let's do some more practice. So given the name, we'll draw the structure on this side, and then given the structure, we'll write the name on this side. So first one, we have hexane. So hex in the previous page means 6, and A and E means only C to C single bonds. So we're going to go 1, 2, 3, 4, 5, 6. That's hexane. 6 carbons in a row, and all of them are connected by single bonds. So heptane, hept means 7 from the prefix table on the previous page. And the A and E means it's all carbon to carbon single bonds. So we want 7 carbons in a row, all connected with single bonds. 1, 2, 3, 4, 5, 6, 7. Butane, the prefix but means 4, and the A and E ending means that there's only carbon to carbon single bonds. So we're going to have 4 carbons, 1, 2, 3, 4, all connected with single bonds. Here we're given the structure and we want to write the name. So we want to find out how many carbons there are. 1, 2, 3, 4, 5. So the prefix that goes with 5 is pent. And then these are all connected with single bonds, so it gets an A-N-E ending, pentane. Next one down, 1, 2, 3, 4, 5, 6, 7, 8. So the prefix for 8 is oct. And they're all connected with single bonds, so this is going to be octane, with the A and E ending to show that the whole carbon chain only contains single bonds. Okay, so what do you do if you have an alkane, but it's not a continuous chain? It has some branches off of it. You got to pick up your pencil to get to some parts of it. Then we have to start naming what are called substituent and alkyl groups. So branch chain alkanes contain more parts. We call these parts the substituent and the alkyl groups. So for example, this branch chain alkane, if I try to trace the whole molecule, I can't get the whole thing traced without having to backtrack. So it contains a branch chain. It has a main chain plus a branch sticking off. So all these parts, the main chain, the longest part I can trace, as well as any branches sticking off of that, they have to be named in a systematic way so that the name accurately describes the exact structure, so that just based on a chemical name, we can make sure that we know exactly what structure that name is referring to. So a substituent is the general name for an atom or a group of atoms that is attached to a chain or a ring of carbon atoms. So if our chain is this chain of 5 carbon atoms, 1, 2, 3, 4, 5, then a substituent off of that is one of these branches sticking off. So a substituent is just a general name for anything sticking off of a group or chain of atoms, a group or ring of atoms. And then an alkyl group is the specific group of carbon atoms sticking off of a chain. So what you do is you look at the alkyl group, CH3, and it's based on what it would be if you plucked it off. That's 3 hydrogens. And that's where it was connected to the chain. If you took this and replaced it with another hydrogen instead of connecting it to the chain, it's named based on what that molecule is. So if you take this substituent, you pluck it off, and you take the spot where it was connected to the chain, you draw in another color, right? That's this bond right here. And you replace the rest of the chain with just another hydrogen. This is a methyl group. And so we call this alkyl group a methyl group. Instead of calling it methane, CH4 is methane, we add the YL ending to show that it's not actually methane, it's not CH4. It's CH4 if you remove one of the hydrogens and attach it to a chain. So there's substituents, that's the general name for an atom or a group of atoms attached to a chain or ring of carbon atoms. And then an alkyl group is a group of carbon atoms, if a hydrogen is removed, that's found connected to the parent chain. So we say CH3 connected to the parent chain, kind of shown here with that bond, CH3 connected to the main chain is called a methyl group. So alkyl groups will always have this YL ending. So if we name this molecule, and we'll go through how to name these, we'd end up calling it 3-methylpentane. The main part of the name is based on the longest chain. So our longest chain here contains 5 carbons and they're all singly bonded. So that's where pentane comes from. And then our alkyl group here, CH3, is a methyl group and it's located at carbon number 3 on the main chain. And that's where the 3 comes from. So we're going to go through systematically how to go from a structure to a name. And then you should also be able to go backwards from a name to drawing the structure. So these are the alkyl groups. They're named based on chain size, and the prefixes follow the same prefixes as used for continuous chains. So if your alkyl group just contains 1 carbon, its chain size is 1, its prefix is meth. But because it's an alkyl group, it's not the main chain, it gets that YL ending to show that it's branching off of the main chain. If your alkyl group contains 2 carbons, 1, 2, then we call that F is the prefix. And because it's an alkyl group, it's sticking off the parent chain, it gets that YL ending. So we call this an ethyl group. So alkyl groups are named based on the length of the carbon chain. And we use the same prefix as for continuous chains, but we add that YL ending to show that it's a branch off of the longest continuous chain. So let's go through rules for naming these things. So the first thing you want to do is you want to identify the longest continuous carbon chain. We call this the parent chain and you name it. So to identify the longest continuous carbon chain, you can take your pen or pencil and trace what's the greatest number of carbons I can trace over without having to backtrack or lift my pencil. In this case, it's 1, 2, 3, 4, 5. And so the parent chain name is pentane. If I drew it another way, I drew it here and down there, it'd still be 1, 2, 3, 4, 5. So you always want to check if there's multiple ways to draw the continuous chain. If I could somehow continue on and get 6 carbons by curving down, then that would be my parent chain, it'd be hexane. So you always want to find the longest possible continuous chain, and it might not always be the most obvious one. So this is the parent chain name, pentane, because it has 5 carbons. In this molecule here, you take your pencil and trace as many as you can without having to lift your pen or backtrack, and we get 1, 2, 3, 4, 5, 6. So the parent chain name is hexane in this case. If we tried tracing another way, let's say we tried going straight across, that might be the most obvious. We'd only get 1, 2, 3, 4, 5 carbons. So that wouldn't be the parent chain. We want it to be the longest possible chain. And since we can get 6 carbons by going around this way, that's the parent chain, hexane. So the most important step, because it's what the rest of the name is based on, is to always find and identify the longest continuous carbon chain. Once you do that, you want to number it. And you want to number it either left to right or right to left, so that whatever substituents are sticking off the parent chain, they're at the lowest numbers possible. So these are the same 2 molecules from the previous page. If we look at the numbering system for the first one, this is pentane. And we have a substituent group sticking off right here. We want to number it so that carbon number 1 on the parent chain, pentane, starts at this end. So we go 1, 2, 3, 4, 5. So that our substituent group is at carbon number 2. If we did it the other way, if we went 1, 2, 3, 4, 5, now our substituent would be sticking off of carbon 4. And so we always want to number these so that the substituents are at the lowest possible carbon numbers that they can be at. So sometimes it'll be left to right, sometimes it'll be right to left. You always want to check both ways to see if one of them is more favorable than the other. Down below on our hexane parent chain, we get the lowest the substituent at the lowest numbered carbon, if we start down here and go 1, 2, 3, 4, 5, 6, so that our substituent is at carbon number 3 on the parent chain. If we did it the other way around, let's say we went 1, 2, 3, 4, 5, 6. Now our substituent would be at carbon number 4. So we want it at the lowest number possible, so it could be at number 3 if we number it the other way around. So after you identify the parent chain, then you want to number the parent chain so that any substituent groups are at the lowest possible numbered carbons sticking off of the parent chain. After you've identified the parent chain and you've numbered it, now you're ready to start naming the substituents that are sticking off. So if there's only one substituent present, you name and locate it by number, and you add a prefix, and then you add the parent carbon chain name as the very ending of the name. So in our first example, our parent chain is pentane, and our substituent group is located at carbon number 2, and it's CH3, which is the prefix meth. So because it's an alkyl group, it's just a chain of carbons. In this case, the chain only has one carbon. It's methyl. It's that YL ending, and it's located at carbon number 2. So we call that 2-methyl. And then at the very end of the name, the last thing you put is the parent chain. So we get 2-methyl pentane as the name of this compound. Down below, we've numbered our parent chain. We know that our parent chain is hexane. And that goes at the very end of the name. And then our substituent is CH3, which is a methyl group. And it's at carbon number 3. At carbon number 3. So we name this 3-methyl hexane. The convention is between numbers and letters, you put a dash. So 3-methyl, because you go from a number to a letter. Between two letters, from methyl to hexane, you don't have to put anything. Okay, so now what if you have 2 or more of the same type of alkyl group present on a molecule? Well, you want to indicate how many you have present using the Greek numerical prefix system. So in the Greek system, di means 2, tri means 3, tetra means 4, penta means 5, hexa means 6, etc. So let's say you have a parent chain of 5 carbons. You've already identified that as the parent chain. Five C's, so it's pentane. And then you identify your substituent groups and you number your parent chain so that the substituent groups are at the lowest numbers possible. And in this case, it could go left to right or right to left. It doesn't matter. They both end up at 2 and 4 either way. So I like to circle my substituents and then identify what they are. So my first substituent is going to be 2-methyl because it's at carbon number 2 and it's a methyl group. And then my other substituent is going to be 4-methyl because it's a methyl group and it's at carbon number 4. Because these are both methyl groups, to make the name a little bit shorter, instead of listing 2-methyl, 4-methyl pentane, we can combine them by listing each of their locations, 2, 4, and then we use the Greek prefix di to mean there's 2 of those. So dimethyl means there's 2 methyl groups and they're at locations 2 and 4. So between numbers, you use a comma. So 2, 4, and then we go from a number to a letter, so then we use a dash. So 2,4-dimethylpentane is the name of this structure. We check out the one on the bottom. We identify our parent chain as pentane. Has 5 carbons in a row, 1, 2, 3, 4, 5. And no matter which way we number it, our substituent groups end up at carbon number 3. So we could do left to right numbering or right to left. And so this is a CH3 group. CH3 group is methyl. And it's at carbon number 3. That's C number 3. And then we have another methyl group. And this is also at carbon number 3. So in this case, we have 2 methyl groups. So we're going to use the Greek prefix di, followed by methyl to mean we have 2 methyl groups. And then we're going to list their locations. And they're both at carbon 3. So we put 3, 3 dimethyl, because we have to list the location of each of these. Even though they're both at carbon 3, we have to list 3 2 times to indicate that of our 2 methyl groups, one's at carbon 3. And in this case, hey, the other one's also at carbon number 3. So the name of this compound, you'd say it 3,3-dimethyl pentane. Okay, so that's if you have, on this previous slide, if you have 2 or more of the same type of alkyl group, like you have 2 methyls or 2 pentyls or 2 butyls. If your substituent groups are identical, that's when you use the Greek prefix di, tri, tetra to show how many of them you have. If your substituent groups are different, like one of them is a methyl group and one of them is an ethyl group, then we do things a little bit differently. So it starts out the same. You always identify your parent chain. So in this case, we have 5 in the parent chain. So it's pentane. And then we identify our substituent groups sticking off of the parent chain. We have one substituent here, and it has 2 carbons in it. So this is going to be an ethyl group. And we have a CH3 group sticking off the parent chain, which is going to be a methyl. So now we need to number the parent chain so that these 2 substituents are at the lowest numbers possible. So here we went from right to left, 1, 2, 3, 4, 5. If we had done it the opposite way, 1, 2, 3, 4, 5, our substituents would be at carbons 3 and 4. So it's proper to have them at the lowest possible number of carbons. So we flipped it so that they're at carbons 2 and 3. So you want them at the lowest possible number of carbons, which is why we numbered it from number 1 here, starting on the right. So now that we know what our substituents are called, we have an ethyl group and we have a methyl group, and we know their locations. Our methyl group is at carbon number 2, and our ethyl group is at carbon number 3. We're ready to put it together into a name. So when you have different substituent groups, you're not going to be using di or tri because they're not identical. You're going to list them in alphabetical order. So ethyl, E, comes before the M in methyl. And so when you write the name, ethyl is going to come first in the name because E comes before M in the alphabet. And just like before, we put the location of the ethyl group on the parent chain, followed by a dash because numbers and letters are separated by dashes. So we do 3 ethyl, that takes care of this one. And then the methyl group is located at carbon 2. So we do dash because we're going from a letter to a number. Anytime you're going between letters and numbers, you do a dash. So 3 ethyl dash 2 methyl to give the location of this methyl group. It's at carbon number 2. And then the parent chain just gets added to the end of whatever the last substituent group is, and there's no space. So 3 ethyl 2 methyl pentane is the name of this compound. The thing to remember when you have 2 or more different types of alkyl groups, like a methyl and an ethyl group, they're not identical. Then when you put them in the name, they go in alphabetical order based on the first letter of the alkyl group. So E comes before M in the alphabet, so ethyl gets listed first, and then methyl comes next. Here's another example. You want to find the longest carbon chain, so you might have to trace this a few times. Like maybe I'd start out and I'd think that This is going to be longest, 1, 2, 3, 4, 5, 6, 7, 8. It actually works out the same because if I went 1 through 8 going down here, then I'd still have a propyl group at carbon number 5. So it doesn't matter. Either way, I end up with a propyl group at carbon number 5. And if I try tracing some other ways, let's say I go down here, 1, 2, 3, 4, 5, 6, 7, that's only 7. So that's not going to be my longest chain. And if I trace down here, it's 1, 2, 3, 4, 5. So that's not going to be my longest chain. So my longest chain is here, 8 across, or it could be here to go 8 down and across. And these two are equivalent because either way you end up with a propyl group, 3 carbons sticking off at carbon number 5. So they're equivalent. So you find your parent chain and you name it. It has 8 carbons, so that's going to be octane. And then you want to locate all of the substituents. And I like to circle them and then name them right away. So this is my first substituent. It has 2 carbons, so that's an ethyl group. Then my next substituent is right here. It has 3 carbons, so that's a propyl group. And then my next substituent is right next to it. It also has 3 carbons, so that's a propyl group. Now I want to number my carbon chain so that my substituents are at the lowest numbers possible. And in this case, numbering from left to right puts them at the lowest numbers possible. We get the ethyl at carbon number 3, and my propyls at carbons number 4 and 5. If we numbered it the other way, 1, 2, 3, 4, 5, 6, 7, 8, we'd have our substituent groups at carbons 4, 5, and 6 instead of at 3, 4, and 5. So you always want to number them to obtain the lowest possible numbers for the substituent group locations. So for my ethyl group, based on my numbering system, I know I'm going to have it at carbon number 3, 3 ethyl. And my propyl, I'm going to have one of them at carbon number 4 and one of them at carbon number 5. And because these two are identical, I can combine them into 4, 5 dipropyl. Di means 2 of them. And they're located at positions 4 and 5. So now when we put this name together, it's based on the first letter of the substituent group. So we're going to be comparing ethyl to propyl. The Greek prefix doesn't count. It's just showing that there's 2 of them. We're going to do it based on P for propyl and E for ethyl. So E comes before P in the alphabet. So our ethyl group is going to be listed first in the name, 3 ethyl. And then you put a dash because we're going from a letter to a number. And we put our next part of our name, 4, 5 dipropyl, 4, 5 dipropyl. And then that's it. We've named all of our substituent groups. And so then we list the parent chain, octane. So you'd say this molecule 3 ethyl 4, 5 dipropyl octane. So let's look at kind of the anatomy of an IUPAC alkane name. So hyphens separate numbers from words, shown here. Hyphens separate numbers from words. So anytime you're going from a number to a word or a word to a number, you're going to put a hyphen in. Commas are going to separate 2 numbers that are next to each other. So anytime you have 2 numbers next to each other, you put a comma. And then when you're going from the parent chain, at the very end of the compound name to the rest of it, there's no comma, no hyphen, no space. The parent chain name just gets added on to whatever substituent chain is listed last based on alphabetical order. So based on this name, our parent chain had 9 carbons. Nonane is the parent chain name. There's a 3 carbon alkyl group located at carbon number 5 along the parent chain. And I know that because I have propyl, and prop means 3. and it's located at carbon number 5. So we have a 3-carbon alkyl group at carbon number 5 on the parent chain. We have a 1-carbon alkyl group located at both carbons 2 and at carbons 3. And I know we have 2 of these because we have dimethyl, and methyl means 1 carbon. And then at carbon number 4, along the chain, there's an alkyl group that has 2 carbons in the alkyl group. Ethyl means 2, so there's a 2-carbon alkyl group located at carbon number 4. So, do you think you could draw this based on the name? Let's check it out. I'm going to open up a whiteboard quick. So our name that we had was 4-ethyl, 2,3-dimethyl, 5-propyl, nonane. Okay, so let's draw this based on the name. So our parent chain is nonane. And that's going to have 9 carbons because nonane, N-O-N, means 9. So let's draw that first. One, 2, 3, 4, 5, 6, 7, 8, 9. I can number this any way I want because I'm drawing this based on the name. So as long as I number it and then I stick with those numbers as I'm adding on these substituent groups, I can do it whatever direction I want. So I'm going to start here with 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's my parent chain. So now let's go through and add on our groups. So let's do 5-propyl first. That means at carbon number 5, there's a propyl group, and propyl means 3-carbon chain. So we're going to do 1, 2, 3. This is carbon 1, carbon 2, carbon 3. So that's our propyl group at carbon 5. Next, let's do the methyl groups. So I have methyl groups at carbons 2 and 3, and dimethyl means there's 2 of them. So at carbon 2, I'm going to put a methyl group. Methyl group just has 1 carbon. And at carbon 3, I'm going to put a methyl group. And those are 1-carbon chains. Then the last part of my structure, 4-ethyl. An ethyl group has 2 carbons. 2-carbon chain, and it's located at carbon number 4. So right here, it's going to have 2 carbons. So 1, 2. This is the first one. This is the second one. So that's that structure. So you should be able to go from the structure to the name, or from the name backwards to the structure. Key things to always check: identify your parent chain, find the longest continuous chain that you can and name it. Then add your constituent chains or substituent chains, put them at the lowest numbers possible, and then identify what they are and place them in the name in alphabetical order. Or if you're going from the name to the structure, once you label your parent chain, you can just place them on the appropriate number of carbons. Okay, let's go back to PowerPoint. So this is kind of a summary of how to name. So you find the longest continuous chain and you name it. This is the parent that anchors the rest of the name. It's going to come at the very end of the name, is where the parent chain comes from. Gets put right here. Then you want to number the carbon atoms in the parent chain so that any branches or substituents are connected to the lowest number of carbons possible. Then I like to circle each substituent and name it, and then list the carbon numbers that they're connected to. This is kind of making an outline, putting all the pieces of my name out there, and then I'll connect them when I'm ready. Then you alphabetize the substituent groups based on the alkyl name. So the Greek prefix like di, tri, tetra, penta, those don't count when you're alphabetizing them. It's just based on the substituent name. And then you put the final name together. You need the location number, the prefix for the alkyl base name, and then the last thing that always comes is the longest parent chain at the very end. So you're always going to have some numbers, the location of the substituents. And if you have a di or a tri, you put commas between those numbers to show all the locations. And then you put a hyphen. And then you put the prefix. And then the alkyl group with the YL ending. And you repeat this for as many alkyl groups as you need to. And at the very end of your name comes the name of the longest carbon chain, the parent chain. So let's name this one. We'll do it here. So first thing, we want to find the parent chain. So I'm going to see, I can go across here, and that would be 1, 2, 3, 4, 5, 6 carbons. Or I could try going here, follow the blue line, and that'd be 1, 2, 3, 4, 5, 6, 7 carbons. If I try one more, I'll do orange. There would be 1, 2, 3, 4. So my longest chain is going to have 7 carbons in it. So I'm going to erase the other ones. I'm just going to draw a box around my longest one so I can remember where it's at. It's this one here. 7 carbons. So it's going to be heptane as the parent chain. One, 2, 3, 4, 5, 6, 7. Okay, next, I want to locate my substituents. I like to circle them and then name what they are. This has 2 carbons, so this is ethyl. And over here, this has 1 carbon, so that's going to be a methyl group. Now I want to number my parent chain so that my substituents are at the lowest numbers possible. So I could go 1, 2, 3, 4, 5, 6, 7. So my substituents would be at 2 and 5 with this numbering system. The other way I could number is I could go 1, 2, 3, 4, 5, 6, 7. And if I did that other numbering system, I'd be at 3 and 6. So it's going to be lower to be at 2 and 5. If you add those together, that equals 7. Versus if I did 3 and 6, if I add those together, that equals 9. So my lowest possible numbering is the one where I have substituent groups at carbons 2 and carbons 5. So let's get rid of the one that I'm not going to use. Okay, I can even color code these. So my methyl group is at carbon number 5, and my ethyl group is at carbon number 2. So I'm going to have 2 ethyl, and I'm going to have 5 methyl. So now that everything's labeled and numbered, I'm ready to start putting the name together. I need to alphabetize my substituent groups. So ethyl comes before methyl in the alphabet. So my ethyl group is going to come first in my name. So it's going to be 2 ethyl. And I'm going to put a dash. And the next part of my name, 5 methyl. And then my parent chain with no dash or no space. And my parent chain is heptane. 2 ethyl, 5 methyl heptane. Okay. This is actually the correct answer. And you know why I got it wrong? I forgot to count one other possible way the parent chain could be made, which is why it's so important to check your parent chain. It's just a classic example of how to do it incorrectly. Okay. I didn't check if this could be my parent chain. 1, 2, 3, 4, 5, 6, 7, 8. So my other parent chain had 7. We ended up with a heptane. This one could have 8. So we need to make this our parent chain. So I went through all that work kind of to illustrate what not to do, because we should have the longest parent chain possible, which is actually 8 carbons. So let's check it out with 8 and see how we arrived at this other answer. So if we have a carbon chain with 8, then we circle our substituent groups. We have one here and one here. They're both methyl. And if we number, we can go 1 through 8 this way. So we'd end up with 3, 6 methyl. Or if we number the other way, 1, 2, 3, 4, 5, 6, 7, 8. We still end up with 3, 6 methyl. So either numbering system works. I'm going to stick with the one in red. So we've identified our substituent groups. We've identified our parent chain. We've numbered the parent chain. We're now ready to put the name together. So we have methyl groups located at carbons 3 and carbon 6, and they're both methyl groups, so we can group these together to make dimethyl. So we get 3, 6 dimethyl. And then our parent chain had 8 carbons, so that's octane. And that's how we get this correct answer here. Okay, so this illustrated again how easy it is, if you're trying to go fast like I was, to misidentify the parent chain. And if we misidentify the parent chain like I initially did, where I identified the parent chain as being this, it messed up the whole rest of our name. Okay, let's do another one. See if we can get this one right from the get-go. Okay, so let's find our parent chain. That's always the first thing you do. So I'm going to try what looks to me like the most obvious one first, but we'll check the other ones too. So if I just draw one continuous line there, I have 1, 2, 3, 4, 5, 6, 7, 8. With the red line, let's try another couple. Let's go blue. And go this way. That'd be 1, 2, 3, 4, 5, 6. Try another one. If I go here and then go down, that'd be 1, 2, 3, 4, 5, 6. If I went this way and down, it'd be the same as going this way and up, because they're both methyl groups. So that would also be 6. Let's try one more. If I start here, go all the way across and then go down here, that'd be 1, 2, 3, 4, 5, 6, 7. So far I've tried quite a few. 8 is the longest, so I'm going to stick with 8. So our parent chain is here. Has 8 carbons, so that's going to be octane. Now off of our parent chain, we've got 4 substituent groups. They're all methyl groups, CH3, so I'm going to circle them all in blue. And these are all methyl too. Now I need to number it so that my methyl groups are at the lowest number of carbons possible. So I could go 1, 2, 3, 4, 5, 6, 7, 8. And if I go the opposite way, it would be 1, 2, 3, 4, 5, 6, 7, 8. So going from left to right, my methyl groups are at carbons 3, 4, and 5. And if I go from right to left, they're at 4, 5, 6. So the red numbering system is the one that's correct. So let's get rid of orange and keep the red system. So now I know that I have methyl groups at carbons 4. So this is 4-methyl. At carbon 3, so I have a 3-methyl. At carbon 4. And at carbon 5. So I have 4 methyl groups. So this is going to be a tetramethyl compound. They're all methyls, so I can group them together and make that tetramethyl. And then I can put their numbers together in front of the tetramethyl. So it will be 3, 4, 4, 5 tetramethyl octane. Good, we got that one correct the first try. Okay, so to give yourself more practice, what I challenge you to do at home is to draw 3 constitutional isomers of hexane and name them. This will get you practice drawing constitutional or structural isomers. These are the ones where the structure is actually different, the connectivity between the atoms is different. And then once you draw them, take the structure that you drew and name it according to the IUPAC naming conventions we just went over. And then do the same thing with pentane and see if you can do it again. So really try this out. It's a really great way to practice both drawing isomers and naming compounds. If you go and you name 2 of the structures you drew, and when you name them, you find out they have the same name, that means they're not constitutional isomers. So if you can name compounds really well, you can always kind of figure out if 2 structures are going to be constitutional isomers, because if they have exactly the same name, that means they have exactly the same length parent chain and branches at exactly the same locations. Therefore, they can't be constitutional isomers because the connectivity would be the same. So get practice with isomers and then use that isomer practice to also get practice with naming. Okay, next time we're going to talk about classification of carbon atoms, and that will lead us to being able to discuss in section 12.11 more complex naming of structures that have a parent chain, branches off the parent chain, and then even smaller branches off the parent chain. So that's the goal, but we first need to talk about classification of carbon atoms. I'll see you then. Thanks for listening, and I'll see you next time.